Sir, the presentation is visible.
Yeah, thank you. Once you are ready, you can let me know.
Yes, sir.
Non-Manala.
Yes, sir. We will start this session. Good afternoon, participants.
Good afternoon.
Good afternoon, sir. Good afternoon, participants. For the third session of day 2 of ATAL sponsored FDP, we have with us experienced professor and an expert who has worked in industry, Professor Muthuraman Ramasamy. And it is my privilege to introduce Professor Ramasamy. Sir has obtained his BE in Electronics and Communication Engineering from Madurai University in 1975 and Master of Engineering in Communication Systems from Madras University in 1977. Sir has vast experience of 30 plus years working in academic institutions and over 9 years of experience working with reputed industries like HP USA, Photo Center Muscat, Sultanate Oman, and Precol Coimbatore. During his tenure in the industries, he has acted as a consultant for electronics R&D and production department of MS Precol Coimbatore, and he was responsible for completing turnkey project for the Ministry of Communication, Agriculture, Fisheries, Finance as consultant and technical chief. He has many honors and awards. To mention few, he was chairman of ECE evaluation for Anna University, member of Board of Studies and Board of Examinations for Anna University, PSG College of Technology. He was also nominee for BOS to government colleges, government technology colleges, and expert member for Staff Selection Board, ACT, Dr. MCT, VLB Engineering College, Chettinad College of Engineering. During his technical projects, he visited various countries like USA, France, Egypt, and Gulf countries. Professor Ramasamy has given many workshops on theoretical as well as practical training sessions to faculties and students on industry projects. So with this introduction, I present to you Professor Muthuraman Ramasamy. Thank you very much, sir, on behalf of the organizing committee, the institute, and the ATAL Academy. I thank you for sparing your valuable time, and you are agreed to give a topic which is very much advanced and now growing, that is on microwave applications in food processing industries. Thank you, sir. Over to you.
Thank you, Professor. Thank you very much for your introduction. You have given a lot about, I don't know whether I had to manage what's the level you have given. I had to go to that level. Okay, thank you for it. I welcome all the participants for this section. Belated wishes for the Happy New Year and take care of your health in this period. So with that, I'll start my lecture. So my topic is going to be micro applications in food processing industries. And in this, we'll talk about general, some concepts behind, and then move into the topic. So profile, just the professor has given me complete detail about me. And just for your information, I've been with this one. You during HP, I was working in most of the time microwave and synthesizers, counters, and spectrum analyzer, network analyzers, and all. And later, I was looking after in India as a coordinator for Indian operations, and I was involved with the VSSC Tumba rocket launch as a standby external expert for supporting rocket launch during 83, 87, and that period. And during member in the photo center as a senior chief engineer of the company, we are able to do the first wireless communication or mobile communication process along with the Telefunken Germany. I am the chief engineer for the project. So we have completed a project at Sultanate of Oman for the government of Oman. So there we have a lot of hurdles, lot of problems, and we have taken about 15 days excess than the committed date of submission of the project. And we have completed the project with 15 days delay, but we have completed as 95% successful. And some of the areas we had some black spots where we are not able to get the connectivity because of the funds allotted to us and the facilities given to us, not able to manage it. So after that, I come back, and then after coming to India, I was with academic institutions. Actually, I do appreciate, I joined the Regional Engineering College at Tiruchirappalli, now NIT, as a faculty in the year 1978. And Dr. Manisundaram was the principal of during the time. I was a faculty, youngest faculty of the Department of ECE. And later I moved to the industry because of my professor was telling your background is good. You can move to the industry side immediately. Later you can back to academic area. So I appreciate all the members who helped me for coming up to this. And thanks the members for attending this program. So food processing. What is a food processing? Why we have to go for processing the food? If you look at it, say we want to extend the shelf life of the products or shelf life of the materials and maintain sensory properties. And sometimes we have to maintain or improve the nutrient contents of the food properties, and we have to ensure safety. For these reasons, we go for food processing. And in this one, we are talking about operations involved. The operations are the raw foodstuffs should be converted to be usable for the consumption or cooking or for storage. So I'm talking about very main important points only, not all points. And food processing, the basic preparation of food, alteration of one form to another form of the food, and then for preservation, how to preserve the food, and then how to pack it up. So we look at the convenience of operations and all, how to carry the food and all these things comes under this topic. And next one, we are talking about why microwave heating is used. The microwave heating can be used for cooking, drying, tempering, pasteurization, or sterilization of foods. So if you look at that, probably we know drying, we know well, by heating we can get the product dried. So that by drying we can have that insects and other microorganisms can be damaged or killed. But in the product, if it is a tempering is a concept of convert the product to be heated to a temperature where the product is having substantial amount of water in the product with form of ice also. So this is the one which you have to do. Heating of ice and water together is one issue. Another one, sometimes they were talking about the pasteurization, which is a form of mild heat applied and destroys the pathological organisms, extend the shelf life of the products. See, in this one, Canada has given a rule or having a stringent rule for 72 degrees Celsius at 1 second, and then you have to cool down. And UK 71.7% degree Celsius for 15 seconds, and then it has to be cooled. So this conditions has to be met with. And in another part is the sterilization process. In the sterilization process, we are having severe heat treatment to be managed, and then microorganisms to be killed completely so that the product can be maintained for a long years. So these are the major requirements of food processing. So next question really relevant to this time. Putting a question: can microwave kill the coronavirus? I think a lot of microwave experts are sitting in this meeting, but I'm putting this issue. Say in 2003, WHO study found SARS viruses can be deactivated by 15 minutes of operations in a temperature of 56 degrees Celsius or 132 degree Fahrenheit, and reduce the aliveness of the viruses by 10,000 times. If you increase the temperature hotter, and the faster the process will be completed. This is the one thing which they are given. And in 2004 study, avian coronavirus, published in June 2004 issue of the Avian Pathology Journal, where an avian coronavirus called IBV was killed after being microwaved for 5 seconds. The third one is 2016, the German study where the HIV virus was deactivated after being microwaved at 800 watts of power for 2 minutes. So under these things, and a lot of ifs and buts are there, but still finally, yes, microwaving your food until boiling about 2 minutes does kill the coronavirus. That's what is the normal conclusion given by most of the people. So heat transfer, how the heat is transferring. So you have the transmission of heat occurs by, normally you know that the radiation can be conduction, convection, and radiation processes. So you say conduction is the thing where the material is in contact, I mean object with the one particle of matter to another particle of the matter, heat is transferred movement of the without movement of the object. So next one is the convection, where the process of convection is the heat transferred by currents in the fluid or gas. You see, cold water comes down and hot water goes up and all these things, which you know that. And heat transfer by radiation is from the sunlight. You're getting to this earth directly. Similarly, heat waveforms or radiation of light energy. An induction process, eddy current loss is used for the induction cooking. So this is the induction process. This are the general heat transfer techniques. So we go for non-thermal process. What is a non-thermal process? Why we have to go for non-thermal process? The main problem with the thermal processing of food is loss of volatile components, nutrients, and flavor. To overcome these problems, non-thermal methods came into food industries to increase the production rate and profit. The non-thermal processing is used for all foods for its better quality, acceptance, and for its shelf life. So main problem with this, which is indicating loss of volatile components, nutrients, and flavor. And main benefits of non-thermal processing is the foods for its better quality, acceptance, shelf life, increase the production rate, increase profitability. So what are the different non-thermal processing methods available? We have high pressure processing, where the items are normally packed in plastic containers or plastic envelopes, and they are kept in a cylinder, and the cylinder is forced inside a water or liquid or water, and it is immersed in water, and it's a 600 times mega pascals or 6,000 times atmospheric pressure is given by the pumping activity, and all these organisms or the virus, all these things are pulled out from this, and the material is processed. So this is one thing. Electron beam processing is something like your electron beam is focused over the packaging, and it is maintained for certain time, depends on the food item and with the power available, and then it is removed. So this is the electron beam processing. Similarly, we can have by X-ray radiations also similar one. Electric field, they what they do is they are having a rods of two rods which is having a high electrical energy applied, maybe in the order of 70 kiloohms volts or 80 kilovolts. And when this voltage is applied, arcing is done. Because of the arcing, the pulses are controlled in the food grains. And the pulse visible light they are using in a xenon lamp for doing the process. The xenon lamp is switched on and off, and during this time you have a white light. All these different frequencies of electromagnetic radiation are available, which are able to kill the germs. And in the microwave, last one is the microwave, which we are going to talk about further. So we are concerned about 300 megahertz, 3300 gigahertz range, and we will be concentrating in the microwave heating process in a particular limited frequencies only. So we'll be talking about 915 megahertz and 2450 megahertz as our microwave heating process. The history, if you look at the history behind, so the microwave is instantly active, accidentally invented by Spencer. Actually, he was having a chocolate in his pocket. The chocolate melted when he was working with the radar systems. So he was wondering why this melting is happening. Then the process started, and this was the invention made was a for microwave oven. So it was produced at 1947, first commercial microwave oven produced and called as radar range. And it is marketed and it was only used for the restaurants and railways and other major companies and not meant for commercial use by the homes. And during 1967, first domestic microwave oven was released in the market after a lot of research because of radiation control has to be made. So the safety hazards have been taken care and it was released during this time. So the microwave oven, what is inside microwave oven? Very simple idea is that this is a picture of microwave oven where you can have on the bottom you have a mobile or rotating plate is available and you have the vents available and the door is open and you can see the door is having grills and the outside glass inside grill is there. The grill dimensions are made in such a way that the microwave cable will not able to escape through this and it will be shielded. So the microwave radiation is dangerous to the body and environment. So they're having I think 5 milliwatt microwatts per kilograms or something they indicated, which you can look at it. And this has to be maintained. So, and here in the microwave oven inside, you're having multiple ways of radiations possible, not single beam. Multiple beams are reflected beams are there because the cavity, actually it's like something like a micro cavity. The entire housing of the microwave oven, inside oven is acting like a cavity of the microwave. So microwave produced from the magnetron, and it is forced inside through the wavegates, and once it reaches this in this one you can see wave stirrer is there which will make the wave going into different directions. So this multi-mode operations is used in this oven. So here the food is going to be kept in the table and the table is going to be rotated. So when all directions you have the microwave getting entering into this and penetrating the food and then goes into the form converting into the heat. So which you can say what are the frequencies of usable. So if you look at the frequency in megahertz, I have given the first column, second column is tolerance permitted, and where the area permission is given. So here it is a 433 start with 2%, maximum 2% tolerance given. Austria, Netherlands, West Germany, Switzerland, and all. Similarly, all these areas given. Different countries have different licenses, but we are most of the time we are going to look at it two frequencies only 915 megahertz and 2450 megahertz. These two frequencies are normally used for commercial as well as for the home microwave oven heating process. So use of electromagnetic waves 2450 megahertz and 915 megahertz to generate heat in material. The mechanism is dipolar interaction. What is the polar molecules? When you look at the water is having lot of polar molecules and two hydrogen atoms and one oxygen atom forming a dipole. And the dipole, like you can look at it. A dipole is made of 104 degrees, two hydrogen atoms and one oxygen atom is combined. And hydrogen atom side is the positive pole and the oxygen becomes negative pole. The sex of water molecules is given as well as the permanent dipole direction is shown. So what will happen when you apply, when there is no external electric field is applied, the water molecules, the dipoles are in different directions, in random directions, but overall it is a neutral value, no directions given. So finally, when you apply electric field, the low frequency or external electric field is applied, the orientation of the polar molecules are modified, our dipoles are changing according to the electric vectors present. So now, if you go and increase the frequency, I'm putting a too lower frequency of radio wave. Now what is happening is too lower frequency of radio wave, the polar molecules in the water automatically modifying. They are changing the direction of positive. When the positive electric field is applied, it is going. When the negative electric field comes, the polar direction changes, which is shown in the figure. And when you have too high frequency of radio wave, yes, they are not able to cope up with the speed and they are not able to orient properly. So in order to do this, any changes we can make. So at moderate frequency of radio wave, that is at the microwave frequencies, they are orienting towards, but in between they take some time or a delay time. After that they orient. So during delay time, they get vibrated and the heat is generated. So this is the time which is microwave. So microwave is able to generate the heat because of the orientation is taking some delay time for changing from one direction to another. So characteristics of microwave heating. So internal heating, it's internal heating. What we mean by internal heating is the conventional heating techniques, the heat is going to go on the material or food material. From external, it slowly go inside and penetrate, and then heat the midpoint or the center point of the foodstuff. It will take longer time for getting heated up. But whereas in the microwave, first microwave itself is a faster fellow energy because speed of light it's going to move, and when it reaches the food particle or food item, and it is enters into the food, and from the inside it is going to come out. So it is internal heating. Heat is generated internally and then it comes out. So this is what's internal heating. And rapid heating, the heating is processed very fast. Conventional heating time takes is much larger because it has to go from the heating point, it has to reach the food. In between, air to be heated up or vessel to be heated up, and all this process will be taking time. So in the microwave, it gets directly to the heating process. So selective heating. So if you're having the cup kept with the water only will be getting heated up, and the cup will not be getting heated up because the glass is made up of porcelain. Some materials are there which are not allowing the heating process, or the heat absorption coefficient will be around 1 by 10,000 or 3,000 times lesser. So they are not getting. So you can have selectively, you can heat the food only and not the vessel. So in this case, the vessels need not be metal. If you are keeping metal vessels or something, they are going to be reflecting the microwave. Microwave energy will not penetrate. So we have to have materials which are allowed. So that's a microwave approved plastics are available, and these materials will permit the microwave to enter into the food. Only foodstuff will be heated up and the vessels will not be heated up. So high heating efficiency. So the efficiency of heating is very high because the microwave penetrates into the object and the speed of light, and object is heated, generates a heat from inside. So it is heated from its own. So this is a heating efficiency is increased. If you look at rapid response and time control, temperature control, the microwave controlling can be done very fast. You can increase the temperature or decrease the temperature, depends on the proper control of the power radiated by the mechanotron, um, which is possible easily. Whereas conventional process would take long time for controlling the temperature variations. So you want to reduce it or increase it, it will take time. But whereas in the microwave, it is much faster. So heating uniformity. So the heating is uniform. Each part of the heated object generates heat. So even for the other objects within the complicated shape, it can be heated reality in uniform. So clean energy is clean because it's said to be clean energy because it does not heat the air surrounding. It is directly heating the material only. So good working and operating environment, it is not be very easy for it, and the cleaning is very much easier. Environment will be kept neat. And if you are using conventional heating techniques, the room will be heated up. It is you have to have the working people will be finding it difficult, but whereas here the working environment will be kept neat. So and it's be clean. So it's a good working environment and operating environment. Next, we look at the dielectric properties of food. Food materials, if you look at the food materials, they consist of lossy dielectric materials. Actually, lossy dielectric materials is they they will act like sometimes they'll act like a capacitor to store some energy. Sometimes they act like a heating material, like a resistance. So it will become a lossy dielectric material in terms of our microengineering transmission. So if you look at this lossy dielectric material, you can have its property. The dielectric properties are going to be decided by determine how well microwave energy can be absorbed. So dielectric property is going to tell how much energy is going to be absorbed from the microwave. And it's going to determine how rapidly the materials will be heated up. These two things are going to be the major one. So dielectric properties in food. So the major factors that influence the dielectric properties for agriculture and food materials are the composition of the material. What is the material consisting of, or the food material consists of? It's maybe consisting of carbohydrates, fat, protein, moisture, salt contents, all these things are there. The food components consist of this carbohydrates, fat, protein, salt content. Now we are having moisture content. So the food already is having a moisture content also there. That water is already there in the food product. And a temperature, the food may be in a particular temperature, maybe very low temperature, or it may be already in a room temperature and all. So and how much temperature you want to increase or decrease, all these things we have to look at it in the processing. And the frequency of oven, what is the type of what's frequency you are operating. As I told you, we are having two frequencies used. So which frequency you are operating, whether each frequency, what are the benefits and the problems and other things. So dielectric properties of food, if you look at it, these characteristics are determined by the complex relative permittivity epsilon r relative to the free space of air. So epsilon r, if we can put epsilon by epsilon naught, which is epsilon dash 1 and minus j epsilon 2 dash. So it is dielectric constant is epsilon dash, and epsilon 2 dash is the dielectric loss factor, which indicates the microwave absorbability. And as if you look at it as if epsilon 2 is high, the product will be heated up easily. If the epsilon 2 is low, will be transparent to microwave and the heating will be difficult. And delta dielectric loss angle, which you are going to look at it, is epsilon 2 by epsilon 1, and is a tan dash delta, and j is minus root minus 1. And dielectric constant and loss factor is important role in determining the microwave with food, interaction of the microwave with the food. Now we look at the dielectric properties of the food again, which say tan delta. What is tan delta? Which will say the tan delta is say 8 epsilon 2 by epsilon 1, which indicated. So there is a very small delta tan angle. Then we can have tan delta equal to delta as it is. We can take it for the expression. And foods do not interact with the magnetic field of component of EM waves, mu equal to mu naught. So we take it as it is. So they are much convenient for us. Only electrical side we are going to look at it. So we look at the other side, further dielectric properties further. In the microwave frequency 2450 and 915 megahertz, the dominant losses are dipole rotation and electric conductivity. So the dipole rotation, we know that it's because of moisture or water content in the product. It is a dipolar rotation or dipole rotation is there. And second part, which is an epsilon sigma, um, is a which is a contribution due to the ionic movements. So ionic electric conduction, ionic electric conduction, where from it is coming? It is coming from the salt added to the food. So we normally add water is there already, some salt will be added, and the salt is going to create a ionic conductivity. So this is again these two uh, points which you have to remember. So later when we are going to go into the discussions, that time it may be much useful. The measurement of dielectric characteristics, how you are going to measure the dielectric characteristics, a transmission and reflection line methods we can think of using. We have the vector network analyzer as the main member. We are having a first, we initially we do the characterization by short circuit, open circuit, all these things are terminations and all testings completed. After that, we put the sample which we are going to have, the measurement sample which you want to use it as inside the tube or the inside the waveguide, and we connect the system, and then we measure the S1, S2 parameters as S11, S12, and the method involves measurement of the reflected S11 and the transmitted signal S21. And the relevant scattering parameters relate closely to the complex permittivity and permeability of the materials. So which you can see the material which I referred. So there you can go into the details and find out how they are doing this process and all. So and the another one is using a dielectric characteristic probe. You use a probe, a coaxial probe for measuring the dielectric. This one in this photo we are indicated a setup of measured dielectric characteristic of a mango. So the probe is attached to the mango, and network analyzer or vector network analyzer is used to measure the value. The measurements of the relative dielectric constant epsilon dash and the relative dielectric loss factor epsilon 2 were performed on the vector network analyzer VNA with 300 kilohertz to 20 gigahertz range you can operate. So the microwave energy absorption is given by molecular structure of the material. So now this chart says on the horizontal line high loss is given, on the vertical line you have low loss. So if you look at each some characteristic have been analyzed and some reports have been given by one of the research paper, one on the research paper I had taken from there, where you see the water is highly lossy, which is closer to the top, and slowly the different ones are coming up. Mashed potato, beef is there, pastry, glass or ice. Last, look at the ice is in the bottommost. So they are in the opposite sides. So the high loss material will heat up faster than low loss material because of the molecules have more space to move around, and thus more heat is generated by friction. But water and ice are on opposite ends of loss chart. And we may be wondering, microwaves used for removing bringing the ice to the water level and then using it for food processing. But you'll be wondering how these two things, how ice is going to be melted. And because ice is low loss member, it will not allow heat to be generated. So how to do this process? This is one topic which will be normally used as a defrosting process. In most of your microwave oven, they'll be having a special program available as defrosting. the defrosting process, which we'll talk about later when you are coming into the slide, which I'll talk about little more detail. So dilatory properties can continuation interaction of food components with water affect dilatory properties, binding forces between protein and carbohydrate and water. If it is strong, smaller values of epsilon dash and epsilon 2 are going to be there. So moisture content of formulating microwave food. So sometimes the food is not possible for microwaving. Adding little water to that will make the food heatable or cookable, which you can add it. So because of the water adding will be able to give support for absorption of the microwave. So here some dielectric constants of various food materials at 25 degrees as indicated. So you have distilled water kept at 77 or 78 epsilon is a dielectric constant, and cooking oil is the lowermost, okay, 2 to 2.5 range. So I have different values are given for different foodstuff, which is actually taken from one of the research papers. And the last factor, again, epsilon 2, which is a dielectric loss, which is going to be the absorption value coefficient for a microwave, which is indicating the cooking oil is having almost 0, and the ham, which is having around 33, 34 value, and all other values are indicated, different levels are indicated. You can have some idea on this. So in this one, dielectric loss is red and blue colors are indicated. The red color um, diagrams are going to be for epsilon dash, which is a dielectric constant, and epsilon 2 indicates in blue color. So if you look at another one, the temperatures are indicated in Celsius degrees, which the top line is at 0 degrees Celsius, and then 20 degree, 40, 60, 80, 100. But what is noticeable is when you increase the temperature of the processing, you are having a epsilon dash or and epsilon 1, both are getting reduced. So if you look at epsilon 1, it is coming down. And in the other side, blue color, if you look at it, you have epsilon 2 is indicated. Epsilon 2 again is a 0 degree in the maximum, and slowly it is got 0 degrees coming around 40. And the value is coming down slowly, and then it reaches approximately, when you look at the wave, it is around 3000 gigahertz. It is getting to 0, and it's a dielectric constant is coming to approximately 1.78, which has been indicated as at around 20,000, I mean 20 gigahertz. So around 20 gigahertz it reaches, which is they say it is closer to the refractive index of water, which is almost reaching there. So now if you have these two details, and another slide, we'll go to the next slide, which you can have some more detail. In this one, if you look at it, so the red one, again, the red one is your dielectric constant, and the blue color indicating dielectric losses. And the temperature increases, the red one is coming down. So the value is getting down, where the dielectric constant value is coming down from 85, 86 onwards. It's coming down around 100 degrees Celsius. It's about 50 or so. But if you look at the blue color, which is again, when you are having a temperature increases, it is coming down very low level. It is coming to 1, 2, 3 and that range. So, and another point, if you notice, where I have given the 2.45, there is a black line indicated, vertical line, which shows the water content. It is not at the maximum epsilon 2. A dielectric loss is not maximum at this frequency of operation of the microwave oven, 2450 megahertz. That is the dielectric constant 20, but whereas the dielectric constant is maximum at 0 degrees Celsius in the blue color, if you notice, approximately around 8000 or 8 gigahertz or so, or 9 gigahertz. That time only it speaks up. So what is the indication of it? At 2450 megahertz, if you're operating your microwave oven and the water is not having full dielectric constant utility, or dipole activities are not much during the time, so some of the water will be getting converted to heat and some of the things will not be doing. So what will happen? The microwave will be acting like a penetration material and go deeper further. So if the top level water is getting heated, bottom will not be getting heated. But now, because of this activity, the water, the microwave beam will be penetrating further inside, and the depth of penetration will be more. So more water in the bottom level also getting heated up. So the footstep will having a water content at a lower level or inner level will be getting heated up with this process. So here, if you look at in the previous slide, we have the dielectric loss was reducing. So when you are increasing the temperature, it is very difficult to heat the footstep. But if you look at this particular thing, that the heading is given as dielectric loss with ionized food. What do we mean by ionized food? Is salt is added to the food. When the salt is added, ionized activity is there. And in our dielectric equation, we have made one component for the polar activity or dipole activity. Another component is sigma one, which we have indicated, that is going to be responsible. So ionized food is going to have the sigma value, which is going to increase the epsilon, which we have seen by the equation. But now here it is we can have a look at this. This is having the blue lines are indicative that even the temperature is increasing, the values are going on increasing. That blue line, if you see a vertical line with an arrow mark uh, next to the 2.45 point, a vertical upward arrow, so that indicates the dielectric constant is going up because of adding a salt to the food material. Same thing is given with the different values of uh, the PPT, where 0 PPT is added. What is the thing, the green color bottom one? And when the uh, salt contents is increased, 5 PPT or 10 PPT, 15 PPT are slowly increasing, we see that the characteristic is going upward. That is means that dielectric loss is going on increasing. So even the temperature increases. If you add salt, depends on the value of the salt content, the dielectric loss will be more. When the dielectric loss is increasing, it microwave heating will be much easier. And this is a indication of the chart with some other research paper has given this detail, which is can see same food. If you look at the cooked beef or something salt without salt, the bottommost line is without salt, and the next line with the salt. That with this thing epsilon 2 dash, that's a dielectric loss factor. It is enhanced because of the addition of the salt in the food. The dielectric value has gone up, so which means processing is be much easier. So here we are having a dielectric properties and penetration depth. See, I am having a chart which is again taken from another research paper, which is they are given some samples. And the samples that say they have first line is a type of food, second one is a temperature involved, and the third one, if you look at third, fourth, fifth combined as epsilon 1, epsilon 2, and penetration depth or the TP. DP is a penetration depth in millimeter given for 9.5 megahertz. And the second part is again epsilon 1, epsilon 2, and DP for 2450 megahertz. Both are given there. So this we are going to another certain things I have got some details which I can just share with you. And the first one is, if you look at these two red circles I made, so the bottom one, if you look at it, who could ham at 25 degrees Celsius and 2450 megahertz operations, the dielectric constant is 72. Whereas if you look at that with 5.5% salt solution of water is 77, almost closer, 77.2 as a dielectric constant at 915 megahertz. Now you see the second one here. If you look at this, again, cooked ham at 25%, 25 degrees Celsius, and epsilon 2, that is the dielectric loss, is 23, whereas distilled water is 10.3 at the same dielectric loss. Here you are having a the releases apple, which you are saving 87.5% moisture, is having a epsilon 2 dash of 11.2, whereas same distilled water is having approximately 10.3. So if you see that apple can get microwave heating much better, 11.2 epsilon dash at 2450. So anyway, EM waves are traveling inside a lossy material. We know that when the wave is entering as a plane wave, which enters there, it is having a angle of incident and angle of reflection. So angle of incident, angle of reflection is equal, and angle of refraction depends on the material. So it is going to the foot material with the eta. So it's, I mean, when it enters with the angle, so what will happen to that? Not the what the refracted ones will go inside and reflected one will be returned back. Now, if you look at it as a cavity, and the cavity is reflected, and the reflected wave will be again rebounding to the foot stuff again. Because this is what's the thing, the cavities are not tuned properly. They have a multi-mode operations are possible in that. Most of the time ovens are on multi-mode operations, except specialized conditions single mode is used. So multi-mode operations, the wave is returning back again, it enters in a different same food in a different angle, it will enters and go into the process for heating. So energy conversion, local conversion of the electrical component of microwaves into thermal energy in foods can be calculated, which assuming the PV is the power conversion per unit volume watts per meter cube, and the frequency of the microwave is in gigahertz, and epsilon 2 relative to electric loss factor, epsilon 0 permittivity of the free space is the electric field intensity of food volts per meter. So the electric field intensity of the food, which is going to be measured, which is relatively very difficult to measure. So the PV, they have a PV value, but one thing we can have it is the power conversion. If you how much power is converted depends on the electrical voltage applied, which is nothing but we can do the modifications as what's the power applied from the magnetron. So it is what is the microwave power you're applying that is going to have it. What is the power going to be absorbed by unit volume of the material? Assuming for volume of the material is V, then probably we can simply multiply total power loss or total power converted by the food material is going to be 2 pi f epsilon naught epsilon 2 dash E square into V, where V is the volume of the food material in meter cube. So this will help some idea because I have not done the research on this, but I have gone through a lot of papers, almost 40, 50 papers I have gone through on this process. So just I can have some idea on this, which can have, depends on the volume of the food material, we have to increase the power of the magnetron. So the magnetron power we adjust to some, when you're having thing calculations are available which you can get, and it depends on the food process you are done. You have to do the epsilon dash 2 dash and epsilon you have to analyze by your own method for each food step you are going to do it in the industrial processing, because normally you'll do bulk processing. When you do bulk processing, you can have few sample processing. During the sample process, all your equations you can apply and do the sample process. Once your sample process is acceptable to the customer or consumer, then you start working in the same thing. Entire batch will be operated in the same conditions. So which you can do it. So increase in temperature of food. The increase in temperature of food to temperature T without consideration of heat transfer is calculated from. So heat transfer I am looking at from the one material to another inside the food. I am not looking at it. That topic is not discussed here. You are just looking at what is the heat transfer. So we have the rho is your specific heat is given as Cp, and rho is given as kilogram per metric cube, and is the density of the material, and you have the voltage applied and then power is applied. Now delta T, capital T is our temperature change, because I told you what is the starting temperature of the food and what is the finishing temperature you require. There is a temperature T, that is a delta T required, and the bottom is a delta small t, which is a time required. How much time you are doing the process. All these things which you have to analyze. So epsilon 2 anyway you are going to calculate, or you are going to measure the epsilon 2 for the particular food product. And with the trial runs, you can know how much power is applied. So that will indirectly indicate what is the E value. So you can find out what is the temperature increase, or for a particular temperature rise you want from say 60 to 80 degrees, you want to make the food more, change. So what is the time required for doing it with this particular power applied, um, power of the microwave oven, so which you can able to spot out. So the microwave penetration depth from the surface of the dielectric to inside is defined as depth that is 37% of the surface power. At 37% of surface power, what is the depth it has achieved? That is called the penetration depth. So which is normally the definition which is indicated. So food material, it goes in the, from the left, it's a from food material, it enters, microwave enters, it goes, and then we measure P0 by divided by E, which is the value. We find out what is the depth. That depth is the penetration depth. So which is the, for food material, the attenuation constant alpha and phase provocation constant beta, the provocation constant gamma are expressed as, you know, the standard electromagnetic EM wave theory, which you know gamma is given by alpha plus j beta is available to us, and alpha is given. This I have taken from the same standard equations for plane wave propagations, which alpha is given, beta is given. And in this alpha, we have modified the alpha value for this particular suiting to this environment. So here we are having a equation inside the second root, epsilon 2 dash by epsilon dash square, which is important. And then the beta. Again, the same thing is there. Epsilon 2 dash, which we are calculating, epsilon 1 dash, we are calculating. Once you know these two things from the food material, we can be able to identify what is alpha and beta. From this, what we can do, we can identify what is the penetration depth inside the food material. So the penetration depth inside the food material is going to be given by power penetration depth in foods is then written as dp is 1 by 2 alpha. Normally dp is 1 by 2 alpha, which we are just equating. We have done already alpha. So the 1 by 2 alpha, which we are replacing. So once you know that, the lambda, you know the lambda can be calculated to beta b by beta. And you can calculate the same terms of C and F. So the F is the frequency of your microwave oven, or the oven you, what is the particular frequency you are having. 2450 may not be exactly the same frequency. It may be plus or minus 50 megahertz. So you have to see that value, what's the value they use. And the dP can be calculated from these equations. So now here I'm indicating some characteristics of heating effect with respect to the frequency. So the x-axis, you're having a frequency, and the heating effect is given in the blue color, and depth of penetration. Now, increase in microwave frequency would give an increase in the speed of heating. Microwave frequency is increased, heating is increased. So because when you go on the x-axis towards your right side, you are going to increase the heating process. Heating effect is going to increase as you increase the frequency of microwave operation. But if you look at the penetration depth, as you increase the frequency, penetration depth is coming down. So you have to have some decision where you have to keep, how much depth you have to have, and how much heat you can generate. So these two things, 2450 megahertz is adequately decided that depth is okay, moderate, as well as heating process is good. So the 2450 was accepted for home microwave oven applications. So in this one, the frequency 2050 is a compromise given the best heating effect against the penetration depth as the chart given to you. So if you look at the chart, and then finally the penetration depth typically in a meat in approximately 1 inch, that is 2.54 centimeters, and approximately 6 centimeters for most of the foodstuffs. So meat is the lowest, 2.54 centimeters. It's from indications or from the details available. I have taken this detail. Now in this one, this chart, the dietary properties, again the same tabulation, I'm bringing it back again, the dietary properties and penetration depth, selected foods. Now in this one, we are not worried about for dietary properties. Earlier we talked about it. In this one, we are looking at the penetration depths on this. So now we see whether we can do something. That again, cooked ham, because I have limited slide. In this slide, I have given only limited footstep. So I had to use one within this limit only. Otherwise, I can have a chart which is not be displayable in single tabulation. So I cut short the table and then trying to use the same. It is the depth in penetration depth, the DP at 2450 megahertz is 2.8 millimeter. Whereas if you are looking at 915 megahertz corn oil, it is having 467 millimeter depth, penetration depth. So this penetration depth of salty foods often cause severe non-uniform heating when using domestic microwave ovens. Because some places what will happen, they talk about something all uh, overheating or heat runaway. Heat runaway is the process. What they talk about is you are having a material which is having some ice formation and some water content, the moisture, high moisture with some ice forming. So you are trying to heat this food in a microwave oven. So what will happen? Some of the water molecules will be readily heated up, and then they try to convert it as a steam. But by the time ice is not yet melted. So what is the thing? One area of the food material is in ice cold condition. Another area is very hot, which is in a steaming conditions. And this particular area will be heated too much, and the other area, icing area, will be very bad, very low heat, or it will be in chill temperature. So this is what they talk about is uh, runaway heating, and this has to be avoided. So in this type of things, defrosting conditions has to be used. So we look at it. This and the next one we see the microwaves at 915 megahertz use industrial microwave heating systems and has 3 times the wavelength of 2450 megahertz microwave in air. So industrial microwaves are 915. So if you look at it, the frequency is approximately 3 times. Industrial microwaves 3 times lesser than the home microwave ovens. Normally 915 is not allowed in the home applications, only 2450. But 915, if you look at it, the microwave is the wavelength is very large compared to 2450, which you know about it. So the wavelength is longer, and what will happen? The penetration depth will be more. So industrial application microwave ovens will be having more depth of penetration than home usable microwave ovens because of this reason that's 2450 is used for in home purposes. So the microwave 915 generally penetrates deeper into the food than microwave 2450, may provide more uniform heating, or can be used to process relatively larger size food particles. So industrial applications, you'll have a huge size of food particles which can be processed, or in a batch processing, you may have multiple stack of food materials kept one over other and can be processed. And home appliances, it's not required. So you can have it at a small one. The microwave penetrations very well in ice at minus 12 degrees because of the extremely low value of relative dielectric loss. So if you look at the ice, so relative loss like epsilon 2 is 0.003, and the depth penetration depth is 11,615 millimeter. This is actually given by some researchers, so which is given as a tabulation is available in the journals. So both these are used in food industry for tempering frozen foods. Tempering frozen foods. What is tempering? Which we already told. Tempering is a process which we are going to have for a small period. We are going to heat it up, bring the temperature to a lower temperature. Sometimes what they do, you have ice or frozen food at minus 40 degree, minus 20 degree. You want to bring down to not to heat it up directly. Instead, you bring the temperature from minus 20 or minus 30 to a temperature of minus 5, minus 4, or minus 1 sometimes. To that temperature, you require this process. So this tempering is used. So once you have a tempering element, so if you leave that after tempering, if you are going to leave the food in the fridge, what will happen? That because of tempering, you are lower down the temperature. I mean, increase the temperature from minus 20, minus 30 degree. It has come down, come up to minus 1 or 0 degree. So if that is the case, now if you leave it without using the food for preparation, then what will happen if you just leave it in the fridge? It's not at minus 40 or minus 30. It is going to be 0 degree or minus 4 degree something. In that case, microorganisms will develop, which is not good for health. So we have to be, if you are tempered, immediately you try to use the food. Or sometimes they'll say thawing. Thawing is the same concept they tell from frozen food to bring down the temperature to a lower temperature. And then after that, you do heating process or cooking process. So either way, if you are not going to use the food, don't make the food for thawing or uh, tempering. So the tempering is normally called as a deep freezing to a sub freezing temperature points. So now look at the penetration depth further. So the value of the microwave penetration depth is a specific food is a good indicator of the ability of the food material to convert microwave energy to heat. This if the dielectric constant are not high, you know that food cannot be heated up. So how to make it heated up? So you had to add some salt. When the moment you add some salt, or already because of cooking you require some salt in that, the salt is there which will increase the dielectric constant, which will help us in, I mean, dielectric loss will be increased and which will help in heating the food faster. Deciding food package thickness of proper microwave heating. So the another one is the microwave uh, uh, penetration depth is going to help us in deciding, assuming you are having a conveyor running with in an industry where you are putting the food materials in a packed materials. I mean, fully packed, and it is a box in a cardboard packing, and the box is moved, or it is shielded in a container, and the container shielded container which will permit the microwave to penetrate. So the container is sent in the conveyor, and the container is having food. Now, what is the maximum thickness of the container you can permit to go inside the conveyor so that the food will be heated properly? Now, your penetration depth is going to give you some idea. So most of the time, your food package thickness should not be greater than 2 to 3 times the penetration depth of the food material. The reason being, we assume the microwave is penetrating from the top layer and the bottom layer and the sides. So what will happen? Maximum depth possible will be from each side approximately one depth it is moving. So we can have approximately two sides. We can have 2 times the depth of penetration. So otherwise, you have to have more time processing required, or you have to do it for a more longer time, or you have to increase the power of the microwave applicator or application applicator. So the microwave penetration depths of microwaves in food of different moisture and salt contents vary widely with the temperature and frequency. Microwave penetration depths are small in foods with added salt. So because we are epsilon 2 or the dielectric loss is increased, so what will happen? Penetration depth will automatically coming down. So for example, the penetration depth of 2450 megahertz microwave at 3.8 millimeter in cooked ham yeah, in this chart you can see the red color. The red circles I have made 2 red circles. So look at the first circle, red circle. It is indicating cooked ham of 25 degrees Celsius, and it is having a depth of penetration at 3.8, and the room temperature, as compared with the 9.9 millimeter in cooked uh, beef. The beef is having 9.9, the same temperature. And if you look at this, both are in the same temperature or room temperature, but the penetration depths are different for the same frequency of application. So it depends on the salt content. So the salt content is different. The penetration depth is reduced for a higher content of salt, and the penetration depth is increased uh, when the salt content is lesser. In general, 915 megahertz microwaves have deeper penetration depth in foods than 2450 megahertz. For the same potato, if you look at it, you have a penetration depth of 915 megahertz microwave, 14.1 blue color. If you look at the blue circles, 14.1, I have a 86% moisture, 1.8 salt, and it's a 14.1 millimeter at room temperature, and it goes to 7.7 millimeter at 80 degrees Celsius. So what is the thing? It indicated 14.1 at room temperature or at 20 degrees has come down to 7.7 depth of penetration at 80 degrees Celsius. That means when the temperature increases, the penetration depth is reduced. When the penetration depth reduced means epsilon 2 or the dielectric loss has gone up. So the dielectric loss is increasing because of the salt at 80%, 80 degrees Celsius is very high compared to the dielectric constant of 20 degree Celsius salt content food. So the penetration depth is more 14.1. So this is again an indicative value to understand what is going on. The microwave at 915 megahertz penetrate deeply in tap or deionized water, in particular at elevated temperatures. And if you have 150, so if you have a superconducting temperature 120 degrees with pressure above 150 millimeters of pressure at 120 degrees Celsius, so the tap water is indicated 120 degrees Celsius temperature, and the penetration depth at 915 megahertz industrial application is 156.2 millimeter. So the tap water at elevated temperature is relatively transparent to 915 megahertz microwaves. So that means it is going up, that the penetration depth is very large, means it's going to be very low epsilon 2. The epsilon 2, if you look at it, very small, 2.5. So it will not be able to uh, heat fast. So this is the problem. So which you are being penetration depth is increased, but whereas the heating process is not possible with that. It will penetrate through, or it will becoming a transparent member. Slowly it will become transparent. Such a unique feature is used in the design of 915 single mode microwave. So this is the thing. This particular one. So you're having a tap water 120 degrees Celsius with 150 millimeter of pressure or greater than 150 millimeter pressure. If you apply 120 degrees Celsius water, then the penetration depth is 156.2 millimeter, which will help you in doing some other applications like sterilization and pasteurization techniques. Sterilization is you are going to have sterilized food. So you have to have deeper inside so that if you can keep this type of arrangement, so you can sterilize the food at a depth or value. So you can have a huge amount of food material and you can penetrate through and then sterilize the food. In this case, you are using single mode operation. That means single particular wave is used, not multi-mode is used. So major components of microwave processing are, you have a simple, so clarity is not there in that. I had taken from some journal, which is not very clear. Please accept. See here, power supply is using high voltage DC. So you require magnetron or magnetron tubes. You require around 3000 volts applicable. and it's in minus 3000 volts is used for the cathode and 0 volts for the anode. If you are having, in that case, you have to generate from the AC power source available from 230. You have to convert the voltage to your 3000 volts DC with a huge capacitor and a huge transformer. Or nowadays you have a SMBS power supplies available with a small size with very high power requirements available. So you can use that. Then you have a transmission section where it's a purely of microwave waveguides are used in this section, and it goes to the applicator, where the applicator is the one which is something like your cavity one, your micro cavity or resonator cavity. So it is not a multi-mode, means you can have multiple frequencies possible, little different frequencies are possible in that. And in the applicator, in the, here you are having a conveyor belt. The conveyor belt is going inside. So in the conveyor belt you are having going to put the materials what you want to do the processing. Food processing materials are kept in this, and the conveyor is going to go at a particular speed, and the speed is decided by how much time you have to radiate the microwave to the food particles. And you know you already done the evaluation process and sample processing, then you know how much time it requires. So that much time it should be a microwave should be applied in that. So if you're having the applicator, sometimes you will not have single source, you will have multiple sources available. Most of the time they'll have 4, 6, 8 and all, so many mechatrons with so many waveguides will be coming in. Each area will be radiated by or irradiated by different mechatrons. So if you're having 8 mechatrons in the assembly line, all 8 one after other it will be heated up. So the conveyor is going to carry the food from one place to another. It is going to heat up continuously, and when it comes out of the conveyor after 8 channel 8 process or 6 magnetron processing, whatever it is required, so it comes out and the material is going to be collected in the collection area. So this will give some idea. So we'll put the next one. This give you some internal details of it. So you have the multi-mode mode stirrer operations, you have the mode stirrers, and you have mechatrons, and you have the chokes available, absorbing loads. You know, one problem will be that when the conveyor is used, you have to be very careful that both sides you should not. Conveyor is going to carry the food. After the food enters, you have to have some locking arrangement that the microwave should not escape from the cavity. The moment it escapes, it's going to be much dangerous because you are going to have huge wattage of microwave power use. Minimum powers in the order of 6 kilowatts up to 150 kilowatts of micro powers are used in some of the applicator usage. So if that is the case, huge power is going to release out. Even a small fraction of the power coming out from the applicator, which is going to be dangerous to the health of the persons. So you have to be careful on that. So absorbing micro absorbing materials are kept in that, and both sides it's kept. And additionally, it's confirmed that locking arrangements are made, and the operators are trained in such a way that every time they operate the machine, they'll be having probe method to test how much is the radiation power outside. So radiating power should be, or leakage power should be checked, and it should be less than the approved norms in the industry. So otherwise, you have to do some process of removing or or rectifying the issue first. So here you having the same thing. Position of the operator is going to load, unload the material. So once the material is loaded, so you'll be away from the area. Most of the time it is happening like that. They'll come out of the area. They won't stand near the machine. Input buffer absorptive materials are kept. So it is a conveyor is going to carry that. And you have waveguide feed from external power packages, cooking cavities there, output buffer of absorbed materials, then it is going to be get released. And after coming out, it is going to be kept for some time for loading area where it is cooled. After bringing it down, then they'll be transferring to the packagings or packing. So here there's a micro power application apparatus is indicated. More power applicator is given here, which you have major source is your macrotron. The macrotron is having there with cooling systems, so maybe having oil cool or water cool or air cool, depends on the power of macrotron used in that. And then you have a huge waveguides coming out. The waveguides are, you know, the normal waveguides, which you remember how to transfer signal. You have the same standard guides available. That guides are going to carry that because it's a 12.5 or 12.6 centimeters wavelength. So you know how much size of the waveguides are used. So the waveguides are going to link the things to that. And when you come in that middle, that red color arrow is going to indicate or indicating the power from the generator is going towards the applicator. And the red color is going from there. And there are two power monitoring meters are there. One is the forward power, another one is the reflective power. You know that forward power should be noticed, which is no applied power, and whatever absorbed by the material balance will be returning back, which is a reflective returning power. So you have PR. So you know that PA, PF and PR are going to be monitored continuously. And if you another one, if you look at the bottom, the reflected power is that you are having a tuner. Why there is a tuner available? The tuner is having a termination tuning adjusting such that the returning power is reduced. So the yellow color or the orange color should be reduced so that very minimal power or no power should be returning back to the guide. So when you monitor in PR, it should be almost zero or very negligible value in such a way that each probe tuner will be tuned, and even if it is escaped from there, it is going to come to your isolator. So you know that isolator property, it will not allow the signal to return back to the source. If it's returning back to the source, it will be dangerous to the source or maybe damaging the source itself. So avoid it. You are having isolator which isolates the power, and then you have in the isolator bottom you will be having a dummy loads or local loads will be available which will take the energy so that no return or reflected power will be returning back to the source, which is taken care. And in order to use that, if you look at the applicator, you have a stirrers are used. So in the moment you have stirrers, you have a multi-mode operation is there, and further turntable is also there. The turntable is there, which is rotating the food materials in different angles, and so that all the area will be radiated by microwave, so that it will be heating will be uniform. That is the thing. So in this case, is the conveyor is not used. It's a turntable process. It's a batch process. Each time you keep it and then take it out from the cavity. Pasteurization, as I told you, it's going to be most of the time used for cooled or the liquid members. The food stuff is a milk or cool drinks or something. They're using pasteurization, which will be they'll be creating heating for a particular time for 5 seconds, 2 seconds, something like that, 72 degrees, and then immediately cool the material. I mean, cool the food material. And this is the thing normally carried by your foodstuff is carried in a plastic container or bottles most of the time. So you're having, if you look at this particular picture, is a material, food materials are filled here, and it is a shielded. The food materials are shielded in a shielding element, and it is gone move to the microwave oven or microwave your microwave chamber, and there it is getting heated up. As per the knobs, it's going to be heated up. After it is getting heated, it is coming down out and then cooled. So it chilled out, later it is cooled and then transmitted out for marketing. So the another one is going to indicate you here. Your loading is automatic. It is going to have conveyor again. So the microwave heating process here, more microwave applicators are available. So it's each one, when it goes through each chamber, is going to be getting it up for a particular time slot. It's going to have each one. First one, T1, T2, T3, T4. Total time or radiation is totally T4. 4 times it's going to be radiated. And you can decide, depends on the requirements, the floor engineering will be done so that they will do that process, sample processing and act. So now this is a holding area. During the holding area, it's little cooled, and then it's going to go to the unloading area where it is chilled for cooled and then transported. So this is a chamber which is going to have normally this one sits there. You're having a waveguides available. So this is one waveguide, second waveguide, third waveguide. Each one is having controls. So waveguides, magnetron power sources available here, and this entire chamber. So you have the conveyor coming out. See, conveyor goes from one side to another side. You can look at the conveyor is carrying the food material. So this is a simple idea which you can have so many photographs available which you can see in the network. See, I just selected some and then used for my presentation. So this is a defrosting. Defrosting is a one process, as I told you, it's a freeze condition food, which when you wanted to heat it up, immediately heating will not be possible. So you have to first bring down the temperature from minus degree to 0 degree or minus plus or minus few 5 degrees or up to so low temperature. Then from low temperature, you do the heating process. So in order to do this, as I told you, frozen food will be having a difficult process in microwave. When you have some area will be in water, some area will be still in ice formation. So how to avoid this? So this particular avoiding is some of the um, ovens are available with the defrost conditions. The defrost condition, what they do is switching on and off. So the microwave power is switched on for a few seconds and switched off. So this will be continued for till you keep the material inside. So you put on defrost condition, it's heating it off, on, off. So what will happen during on condition? Some of the water molecules will be heated up heavily. Then before they go into steam, they are at a higher temperature. Before they go into steam, they switch off. Power is switched off. So once the power is switched off, now the hot water nearby is going to do uh, the convection process of heat transfer, and make the nearby ice molecules be converted. So they becomes water. Now once all this becomes water, then the process is going to be simply removal of water vapor. That is easier, which will have dipole polar activity can handle, and that will make the food heated up. So this can be used for this type of thing for the pasteurization. For sterilization, uh, you are going to have the similar technique. The sterilization is one which you are having a achieving preservative free yet microbiologically safe products. What's the preservative free? You can have chemicals added for preserving the material without or pest controls and all, but the chemicals are not usable. So what you can do, you can avoid it. So microwave can help you. In all forms of packaging, powders, liquids, pasty, bulky, and packaged materials you can do. Without removing the package, you can do this process. Pasteurization or even ready meals can be used for with packing materials. You can do the process, and substantial reduction of microbiological load is achieved by this method, and high-speed process that can be carried out continuously with a significant logistics of handling and production scheduling properly done. You can achieve very fast material transaction in this microwave heating techniques. So which you can make the microwave usable continuously. The factory can be continuously on. Only thing, logistic to be maintained properly. So today's challenge, if you notice, today's challenge is the destruction of mold, bacteria, and other insects colonies without the use of toxic chemical products in the main concern. That is the main concern for us. You should not use chemicals for controlling the pesticides. So the process consists of a short exposure of the product to a microwave within a temperature controlled processing cavity. The temperature of the cavity, the intensity of the field, and the process duration, and the selected according to the food ingredient and the type of waste to be eliminated. Process time will determine the level of inactivation. The process, which lasts only for few minutes, ensures that the product is brought quickly and uniformly to the required temperature. The processing time is short enough to prevent alteration of the physical, chemical, and organochemical characteristic of the products, food products. So taste and other things will not be modified much. So this is actually used for the food grains. So you have this food grains, pest controls, and microbiological or enzymes destroying everything. You can do this with this type of things. It will be the temperature. Again, as I told you have to measure epsilon2 and epsilon1 and sample run. Then you decide and then make bulk running, and you can have bulk processing. And with the measured power and measured time, you can able to do this process. Another few minutes, I try to complete it. Sterilization, conventionally processed one, and this is a microwave sterilizes salmon and rice. You see, the quality is maintained as it is, whereas in the can type, you can see the difference. So the uniqueness in a microwave sterilization technology is that it can be applied to both solid and liquid foods, as well as complete meals sealed in multi-compartmental trays. With the tray itself, we can do the process. Sterilization is possible to do it. So in-package microwave sterilization products are currently available in the market. In Europe, it's more very much available. Microwave products include different items, pasta, rice dishes, main dishes, etc. are available. Rapid food cooking is one which is normally used without, say, if you are using conventional cooking methods, the crust will be formed on the top layer. So you'll have inner layer will not be heated up, outer layer will be, crust will be there, or the black color or dark color will be formed. But in this one, it's not. There is a sample taken from one of the papers, the rapid food cooking by means of microwave ovens. So these are the references I used. Most of my references are given, and I have used some more references which I given major area which I referred. So these are the references which I've gone through for making my presentation. I had to thank all these reference authors or the research members, which their papers have helped me a lot in preparing for the presentations. I thank you very much for your patient listening to me. I don't know whether you are able to receive some material from me so far. I don't know. I'm waiting for comments. My contact details are given in the details. Thank you for your listening. Thank you, Professor. Thank you very much for giving me an opportunity to be with you and do a presentation. I'm thankful to all of the members.
Thank you, sir. Raghavan, sir.
Yes, sir.
Are you there online?
Raghavan, sir, very, very nice to have a contact to you. Actually, I know about you. You are from NIT. Actually, Soma Skandan and myself, we have been working together well in 78 region. After that, I moved out to industry, and he was continuing there till last 2 years back.
Oh,
see, we are
in the chat box. I have written whether you remember me. I am contacting you after 20 years. Very happy.
Yeah, I have not noticed. Actually, I have not seen the chat.
With the permission of the organizer, Dr. Datta Prasad, I want to take 2 minutes.
Yes, sir, please.
First of all, most of the participants have expressed wonderful comment on your work. Really, you deserve a lot, and the person who arranged also deserve a lot. And every lecture is better than the previous one. It is unique, not from the academic point of view, academic plus practical point of view. I got some 2-3 questions I have put in the chat box. Many are not able to give answer. I think you are the correct person.
Even I don't know. You are the best. The man of the day. Actually, the top man of microengineering. I don't know how to answer your question.
No.
But anyway, I may best
this
to
one,
do it.
You are the only person. See, it is a technical sentence. Some may even say it is a controversial sentence. They say microwaves are friendly with women. The take-home story is, if man cooks with microwave oven, some harmful effect will happen. But women cooks with microwave oven, not that much harmful. Am I correct?
I don't know whether you are talking about the food is harmful or the person is
to the person, not food. The person who is cooking with microwave oven, that man will be more harmful. Affected.
I mean, he get more radiation probably.
The radiation to men is more harmful than radiation to women.
Yeah,
Um,
probably we can argue. I think the immediate answer I may probably think about it is the body details. But if you look at the body, probably the Epsilon effect may be there, dielectric
uh,
consent.
you
That
you
may
are
be one of the, probably we have to look at it. What is real?
it is not probably. You have given exact answer. I wanted to confirm through a person like you, because people talk microwave oven, they may not be good in both technical and you. I know about you. I have seen your photo in the department. So it
Oh,
is
so many years we are maintaining it.
it is maintained, heritage photos.
Ah,
And
because I remember that old days. I
uh,
start my class at 6:30, 8:30.
uh,
After that, I'll be free. I do a
Ramakrishna
lot of
Rao,
work in the
they
lab
used to
working.
tell you. Now today only I got the opportunity to
Yeah,
that.
Rao was very close friend of mine, and actually he was a guide for me. Complete
Okay.
guidance he was giving me.
Anyway, second thing, maybe on behalf of the participants, I'm asking, how did you gain this much practical knowledge of microwaves in the food industry?
Uh, Purely, sir. Actually, I wanted to do some work on that. I have been looking at a lot of journals I've been reading. So I had got a lot of material prepared. So for preparing this material to this section, whether you agree with me or not, maybe I'm not that much expert like you, but I took almost 10 days for processing this material.
No, no, it is wonderful,
Took
wonderful.
10 days to make this material. Even then, still I'm little, somewhere I'm getting little hesitation to argue. Some points, not immediate. So it requires some more practicing for me to um, I mean, refer few more articles in this area.
No, no, I
Lot of
can.
articles are available, but most of the time, see, engineering college teachers or technological college teachers are not. We are looking at the microwave application, not in the other applications we are worrying about, not in the food processing industry, but it's a huge sector. Lot of, because food processing is every time required. But lot of our engineering, engineers in the engineering colleges, process, we are not concentrating our attention to food processing area.
Okay,
Actually, the food processing area is most of the time it is taken by agriculture scientists and agriculture professors. But
okay.
they have limited knowledge in microwave and RF area, so they are not doing a lot of work on this. But in foreign countries, I have seen a lot of papers coming out, which is all from agriculture university papers. So technological university, food technology, and agriculture university only they are doing lots of research on microwave applications industry.
I
But we are
can.
looking at industrial products and they are looking at food products.
I can
So they,
authentically say in this field you may be number one or number two in India. I can
no,
authentically
sir.
say in
There
front
are
of
some
many
excellent
people.
experts are available. Experts are available in Bombay. Some Ahmedabad, some people are there, very good people. They had every day, day in, day out, they are doing this process regularly.
And
So they may be the highest people on this area.
I wish you.
I am a small boy in this area,
No,
just growing up.
big people tell like that only. But one small thing, only one more minute I am taking.
No, no, you take
No,
it.
no, I am getting the permission from Dr. Datta Prasad.
Yes, sir. Sir, actually, I will take the credit to reunite two old colleagues.
Oh, it is 30 years old.
Thank you, sir.
And
Please
we
30
continue,
years
are
sir.
old, sir.
and
30
we are
years old.
theoretical person, whereas he is theory plus practical. So participants should ask more questions. Sir, once again, one more thing, you should visit CFTRI. They will
Yeah.
highly benefit from you. CFTRI and also Agriculture University Coimbatore, both
Agriculture
when
University, Coimbatore, yeah.
both will get highly benefited by you, and you will be made known to the world. Now, I request, I open the participants to make use of the very rare opportunity. You cannot get a person of
Well,
micro knowledge in
Dr. Dutta, can I
practical
close
thing.
the slide? Can I close the slide and come to the video mode?
Yes, sir. Yes.
Okay, I wish participants ask all kind of questions, what you normally ask a theoretical person. Okay, thanks to Dr. Datta Prasad.
Thank you, sir.
I have to thank him for giving an opportunity to meet. Actually, when I see that Raghavan name is there, I was wondering, after so many years, we are guys going to talk to some big man. Something great, sir. You remember me after so many years. That's a great thing. I think I had to appreciate my friend, Mr. Ravi. the previous presenter for me. Actually, we have been together for microwave work. Actually, he is trying to do some lot of work on microwave generations in the actually gig oscillator. He is trying to do it. We are trying to work together and generating Zik oscillations at the lower cost.
To be
So in his
frank with
products,
you,
he want to make.
He is one of the participants who was keenly watching your lesson. And when I posted the question, I found him smiling.
Oh,
smiling
he's watching.
He's watching, listening, understanding
watching
everything.
Thank you, sir. Thank you
Oh
very much,
my
sir.
God! My God! Right. See, he was the person who has introduced me to Dr. Datta. I had to appreciate Mr. Ravi for helping me and making me to link to Datta Prasad sir, so that he can put me as one of the member.
And
I think
what
Dr.
I,
Datta Prasad, I have made your expectation, or at least to the level required.
more than that.
Yes, sir. Very more than it, sir. Yes, sir. Thank you so
Participants
much.
have written, what a wonderful session, like that they put. And the last thing, my wish is if Professor Ramasamy and Professor Ravi Kumar join together, wonders can be done. The radar can be brought
We are
to
trying
the
to
footing.
do it. Actually, we are already doing some discussions on that.
Yes, sir.
Not a beneficial on the we are looking at the technical advancement we have to make so that we can reach universities and colleges at the lower cost we can achieve, so that education sector can able to buy and use the facility for the student education process. That is what we
Yes,
are looking for.
that's really
Already
great,
he
sir.
is doing a lot of work on that area, micro area, which I am trying to involve with him, so that my small knowledge can be added to his product so that it can be improved further.
Now, I wish Dr. Datta Prasad allows 5-10 minutes to the participants.
Yes, sir. Yes.
Many people
Sir,
are eager to ask
Ramasamy,
questions.
sir, I can see one question in the chat box asked by Mr. Anup. He says, wonderful session, sir. Whether microwave is used in quality assessment of foodstuffs in industry. I remember reading somewhere microwave interferometry is used in estimation of dry rubber contents in rubber latex.
Yeah, actually, in microwave, they are using for lattices, rubber manufacturing process. They are using microwave. Actually, microwave heating process we used for this one. No, your what is the thing? That rubber tire manufacturing process, a top layer fixing, galvanizing techniques, and other things. They are making use of it. So already they are using this technique. Wherever you require huge temperature requirement or controlled temperature, controlled time, then definitely you can think of microwave. Only thing you will not be happy the food industry or the women folk will not be happy with microwave is they cannot make a crust out of food because it is not formable. The microwave oven you won't get a crust unless if you are packing the material in a normal conventional oven or in a hot plate, you can get the crust formed. The top layer will be very dark red or something, but that is not possible in microwave oven process because everything will be in uniform temperature. So that some people will not like microwave for cooking. Otherwise, it is good. But there are dangers which that you have to take care, that radiation process, radiation effects, which you have to be careful. You are in a radiation environment, which you must remember about it. That always you must keep in mind. So if you look at the microwave oven, you have a lot of safeguarding techniques that are there. The moment you open the door, system will not function. Even if the microwave is not switched off, these locking arrangements are there which you cannot open the door. But still, by mistake, you are opened, immediately microwave will be stopped. You have controls. So safety controls are there. And if the temperature of the microwave oven is going up, there's a fan control which will stop the system. And now lot of facilities are added to the software controls of the micro engineering, micro ovens, where you can have uh, radiation is not there. Even if the later, some people check with your mobile phone itself, radiation effects can be monitored. That will indicate what is the radiation effect. But the moment you once you switch on the microwave, be careful. You be away at least 1 meter away from that night. Corona Martha. Just like Corona, be 1 meter away from each person. So from 1 meter away from the microwave oven, your radiation effect will be reduced to approximately 1,000 times. So which is a huge thing. You don't stand near the microwave when the microwave oven is on. Even in a kitchen, if you're having that facility, just to see that you have enough, at least 1 meter distance away, you have an area of working for the microwave. So microwave should be 1 meter inside, then you will be safer. No radiation effect will be affecting.
Hello.
So probably
Ready,
as Raghavan sir was telling, dielectric constant other area somebody has to work, or you have to search for papers whether anybody has worked on that area. Health hazards of microwave engineering for differential between women and gents, whether any topic is there, or probably somebody can start the topic and then work on that research area. It's a good practice area. Okay. Yes, sir.
Sir,
Yeah.
I don't know
actually,
whether I have answered the question. I don't know
sir, we
whether I answered the question. Anu was asking. Hello. Hello.
Yes, yes, sir. It's clear.
Okay.
Okay. Thank you so much, sir.
Any other people? Any
If you
comment?
have any questions, you can post in the chat box, or you can unmute and ask.
Yeah, no bad too.
Can we conclude the session, sir? Raghavan, sir?
Yes, please.
Yes, sir.
Technical, that's Ravi Kumar, sir. What is the comment, sir? Technical lab, Ravi Kumar.
sir, actually, we are working on that. Yes, sir. Can you hear me, sir?
Yes, sir.
Yeah, I am able to hear. I'm not able to see you.
We are trying to develop one microwave moisture meter,
Yeah,
which will be used in the food industry.
yeah.
And also, you can determine the moisture content in concrete blocks.
Ah. See, the moisture meter is also again one
That will
more
be very,
thing which is required, because in our I mean, when I am presenting the tables, I mean, charts and all, you would have noticed the moisture contains 80%, 86%, 70% and all. And I told you another point, which is how many people remember. The food is not heatable, then you can add a little water to that, then it will start heating up fast. So you microwaving, when you are doing, add little water to the food content, that it will be heated up fast. Adding water, it will becomes a polarization process will be activated. You will be getting the material heated fast. Otherwise, heating will take longer time. So this is a thing. So moisture content measurement is very, very important when you are doing the process in the industry. Then only you can decide what's the power level required for doing the process,
okay, sir. Thank you.
right?
Yes, sir. Thank you.
Yeah. Choose Mr. Datta Prasad. Now your turn. You can decide.
Yes, sir. Thank you so much, sir. On behalf of the ATAL Academy, which has sponsored this FDP, our institute, which is KLS Gupta Institute of Technology, all the participants, and on my personal behalf, I thank you for sparing your valuable time and giving a really wonderful session on microwave applications in food processing industry. And in fact, it was, as rightly mentioned by one of the participants, it was very happy moment for us to witness reunion of two legends in working in the field of microwave industry, sir. It was really a great moment for all of us to witness. Thank you so much, sir. We see a continuous support from you while working in the field of microwave and antennas. Thank you, Ravi Kumar.
Yeah. Anybody require any help? I can give me a technical. I mean, fundamental analog and an RF and probably microwave. You can, if you are requiring any support, you can call me. My number I given, probably you would have noticed it.
Yes,
And you
sir.
can contact me. My email ID is there. If I'm not able to immediately answer, at least give me some time, burden with me. I will try to do some work and then return back, because I will not be an expert for everything. So certain times I might have to go through my fresh up my mind, or my uh, mentally I have to fresh up and then get ready. Then I can probably discuss with you on the topics. You
Yes,
can
sir.
call me for any presentations or any faculty training or any student training workshops. I can do workshop with the practical and theoretical side, which actually Ravi Kumar sir and myself, we had done one workshop at I think ACM or ASM college at Bangalore for faculty. which was really so much time. They want 10 days workshop, but we were given only 3 days. But finally, every comment was made that they have to be given 10 days time for training all the faculty in this theoretical and practical, both from the fundamental, from analog circuit, for electronic circuit 1 onwards up to microengineering, practical and theoretical discussions. Theory, we won't go for equations and all. We'll give the concepts and then applications. Then we go to the practical section where some of the topics will be handled by me. Some topics Ravi Kumar was handling in microwave oscillators, microwave transmissions and all. He was talking about satellite communications and all. So we can able to work together, and few more people if we join, probably Ravan sir is also joining. We can do a lot of technical training sections, which theoretical, practical merged. That may be
Yes,
useful to students as well as young faculty members, not the experts. Young faculty members may get gain out of it. So we are
yes.
looking at the possibility. I think I can. This reunion of Ravan sir may help me in joining with him again. Thank you, sir. Thank you for all the participants for listening to me for 1.5 hours plus. And
Yes, sir.
I again appreciate Mr. Datta Prasad for calling me and Ravi Kumar sir to introduce me to him. And thanks to everyone. Thank you for all of you.
Thank you, sir. Thank you
Thank
so
you.
much. Thank you, sir.